Hi, everyone. I am Tan Tao from School of Artificial Intelligence, University of Chinese Academy of Sciences. I also study in the Institute of Automation, Chinese Academy of Sciences. I am delighted to share our work, Occlusion-Aware Neural Domain Adaptation for Self-Supervised 6D Object Pose Estimation. 6D object pose estimation is a challenging task in the computer vision field, which aims to estimate object poses from single images. Some typical works in literature attempt to translate the synthetic images with object pose labels, generated by object CAD models, into the real domain, and then use the translated data for training. However, they generally have the two limitations. Firstly, there still exists a significant domain gap between the translated images and the real images. Moreover, the translated images cannot sufficiently reflect occlusions that exist in many real images. In this work, we propose an occlusion-aware neural domain adaptation method for self-supervised 6D object pose estimation, called ONDA-Pose. Our method firstly translates unlabeled real images into the synthetic domain. The pose estimator is supervised, using real images along with the translated images and pseudo-pose labels. Our method has three main contributions. First, we explore a CAD-like radiance field to generate synthetic images and masks aligned with unannotated training real images. These synthetic images share the same object poses as the corresponding real image. Second, we design a global object pose refiner, which can globally refine the initially estimated object poses to generate accurate pseudo-object pose labels. Third, by jointly utilizing the CAD-like radiance field and the global object pose refiner, we propose the ONDA-Pose method for self-supervised 6D object pose estimation. Its effectiveness in narrowing the domain gap and handling occlusions is demonstrated by the experimental results. Our method comprises four main modules: an object detector, a CAD-like radiance field, called CARF, a backbone pose estimator, and a global object pose refiner. First, the synthetic image and mask are rendered from CARF using the calculated camera pose. Then, the pre-trained backbone pose estimator is used to estimate an initial object pose, which is further refined by the global object pose refiner to a pseudo-object pose label. Finally, the pre-trained backbone pose estimator is self-supervised using the cropped real image with the pseudo-object pose label, the synthetic image and mask, by leveraging a differentiable renderer. The CAD-like radiance field consists of two multilayer perceptrons, referred to as the geometry block and the radiance block respectively. First, the geometry block is pre-trained using the real image with the predicted masks and the camera pose to learn the accurate geometric information of the real object. Then, with the geometry block frozen, two radiance blocks are supervised, with the synthetic image rendered from the CAD model and the camera pose to learn the texture information of the object's CAD model using a patch-based training method. We propose a global object pose refiner that leverages the calculated camera poses to improve the accuracy of the initially estimated object poses. For an arbitrary 3D object point, the object pose and the camera pose determine the spatial transformation between its coordinate under the object coordinate system and its coordinate under the world coordinate system. Taking advantage of this feature, the global object pose refiner leverages the calculated camera poses to improve the accuracy of the initially estimated object poses by minimizing an objective function. The total loss function of the proposed network contains three loss terms: a point matching loss, an RGB similarity loss, and a mask similarity loss. The point matching loss geometrically aligning the estimated object pose with the pseudo-object pose label. The RGB similarity loss maximizes the similarity between the synthetic image rendered from the CAD model via the differentiable renderer and the synthetic image rendered from the CAD-like radiance field. The mask similarity loss align the mask R rendered from the CAD model via the differentiable renderer with the mask rendered from the CAD-like radiance field. To evaluate the performance of our method, we conduct experiments on two common datasets. As shown in the first table, our method achieves better performance than all other methods that trained without annotated real data and even outperforms three fully supervised methods on line mod dataset. Moreover, as shown in the second table, our method also achieves the best performance. The visualized estimated results on occluded line mod dataset also demonstrate the significant performance of our method on pose estimation and domain adaptation. In conclusion, we have proposed the ONDA-Pose method for self-supervised 6D object pose estimation. Firstly, we explore a CAD-like radiance field to translate unannotated real images into the synthetic domain, which is proven to effectively reduce the domain gap and boost the performance on 6D object pose estimation. Then, the backbone pose estimator pre-trained on synthetic data is used to estimate initial object poses for the real-to-synthetic translated images. Meanwhile, these initial object poses are refined by the global object pose refiner to generate pseudo-object pose labels for the corresponding real images. Finally, we further self-supervise the pre-trained backbone pose estimator by utilizing real images with pseudo-object pose labels and the real-to-synthetic translated images with the corresponding masks. The experimental results demonstrate the effectiveness of the proposed method. Thank you.